In this video, we're going to address general polynomial functions. So we looked at linear polynomials, quadratic polynomials, and now we're looking at the general case. So again, this is the definition of a polynomial function, right? It will always have this form. We've talked about this already. So if it's a cubic, it would be p for polynomial, n would be 3. So it would be x to the 3, right? X squared, x to the first power. And this would be 1, a0 times 1, and 1 is x to the 0 power. Now, we had this factorization theorem with the quadratic. So we had quadratic factorization when there was only, right, n would be 2. So the same thing holds in general, right? If it was quadratic, there's an x1 and an x2. Now there's more terms. So if it's a cubic, you'd have your constant, your first term involving x1, your second term involving x2, and so forth, your third term involving x3, and so on and so forth. So you saw that the factorization theorem for the quadratic was just a special case of this. The key difference here is for a quadratic, you can actually come up with a form, the quadratic formula, to calculate x1 and x2. The difficulty here, and it is a real problem that we're going to look at next, is that we don't have a formula for calculating x1 and x2. In fact, it's very challenging in general. So that's a difficulty. We don't have a satisfactory answer for that. Okay, but I can factor a polynomial. I'm going to refer to this form here in the definition as the global form, and you'll see why. And this form as the local form. And again, we'll talk about that. Okay? Again, just as we had with quadratics, we can define a zero of the polynomial, and that's a value, an x value, such that when you plug in the value, the polynomial equals 0. Y is 0. Okay. Now we don't have any concept, we don't have vertexes, we can't just have a formula vertex. So as I said, to get a fully satisfactory answer here, you kind of need calculus to make up for the differences. So we'll see what we can do, but we're going to have an incomplete picture. But what the factorization theorem says is that an nth order polynomial function has n zeros. So a linear function has 1 0, a quadratic function has 2 zeros. We can get them from the quadratic formula. A cubic function has 3 zeros. A fourth order polynomial has 4 zeros. Now you have to understand the caveat. If it's nth order, you have n zeros. The caveat is that these can be real numbers. They can be repeated, right? So you could have 1 being a 0 twice, right? It can be twice. They can be repeated. Or they can be complex numbers. In fact, this is where complex numbers really made their appearance, so that you can say an nth order polynomial has n zeros. If you allow complex numbers, it's a nice clean expression. And that was the motivation for complex numbers. So you have nth order polynomial always has n zeros. They could be complex. Okay, so again, we'll see. Here's a typical one, and we'll see the issues here. Okay, now this is just a quadratic, but I'm going to look, so we can do this just as the last section. In the last section, we would find 2 zeros if we needed the quadratic formula. And we'd find the vertex, we'd plot those 3 points, and you should be done. It should be that straightforward. This is not an hour-long problem. But let's look at this as we're going to look at a general polynomial, okay, and see what we have. So it'll be a quadratic. Let's look at it. So I'm looking at the function, and I'm going to look at the global form. Right, here it is. And you'll see the distinction. But I also want to be able to factor this. Now again, generally this is a problem. This is a huge problem. So I want the global form and what I'm going to call the local form, the factored form. Okay? Now in this case, it's a quadratic. It does factor fairly easily. I could use the quadratic formula. In general, this is going to be a very difficult step. Okay? So I'm just going to caution you. Now I want to write it as an equation in the usual way. Right? So y equals the function f of x, or in this case p2 of x. Now the solution set, it's a question, where do I get the points? Where do I get them? That's always the question, right? They're infinitely many. Now, for a quadratic, of course, we knew the zeros in the vertex. But let's just assume this is a general one. What's the game plan? Well, I'm always going to use zeros. I'm always going to find the zeros. Why? Because that's what the local form gives me. That's the point of the local form. So zeros are going to be in the neighborhood. That's why it's called local versus, we'll see in a minute. So zeros are where the function equals 0. And again, see how the local form just gives it to me. The local form, it's always going to be a times b equals 0, or a times b times c equals 0. That's what the local form gives me. It always gives me the zeros fairly easily. It's hard work getting the local form, but once I have it, I get the zeros easily, right? A times b equals 0, a is 0, I know b is 0. So you see I have a is 0, b is 0, right? X equals 3, x equals minus 1. So if I have the local form, I can always get the zeros. So I have those points available to me. See, I can put them in a set, in the solution set, right? And again, notice I know what the y values are. What are they? They're 0. I mean, you can plug them into the formula, but they're just zeros. That's how we got them. They're zeros. So I can always get the 0. If I have the local form, if I have the local form, I can always get the zeros easily. And that's fine. Those are a couple of points you really want. Okay? Now the question is, where do I get the other point? I don't. In general, I don't. I can't get it. Again, you'd need calculus for that. But okay, what can we do instead? What can we replace? What can we use as a replacement for this? What can we substitute? I mean, this is a little more. I don't have the vertex, right? Well, I do. It's quadratic, but let's say we don't. All right, so I don't have a third point. But we still have to do something. What can we do? We can do asymptotes. And for asymptotes, I need the... Okay, what is an asymptote? See, an asymptote is, the local form means it's in my neighborhood, right? 3 and minus 1, they're kind of close by. Asymptotes, I think it comes from, think about sitting up in the crow's nest of a ship, 500 years ago and you're in the middle of the Atlantic. What you're doing is you're sitting up there looking to the horizon trying to find land. That's what asymptote means. I think it's ancient Greek or Latin. It says something. It means looking far away, staring out into the distance, okay? So I'm trying to see what's happening in the distance. As x gets large, I want to see what happens to y. Now again, don't make this a big deal. Look, this should be very quick and easy, or we don't do it. Don't make every battle hard. Let's go through how you do it, and you should be able to do this very quickly. So x has to go get large. See, I'm looking at the horizon. So what's the trend? 1, x is 1, x gets big as 10, x gets big 100, x gets big 1,000, x gets big 10,000. That's what we mean when we say ... we go to infinity. I mean, infinity is not a number. Infinity means this trend. I'm trying to predict what happens when I look to the horizon. Well, look at the y values. Check this out. This is pretty clever stuff, and it makes it easy. I mean, you think everything has to be hard algebra, like that solving rational equations. I mean, okay, this should be straightforward. Okay, so I want to estimate the trend with the y values. That's what I'm trying to do. That's what the asymptote is, this trend. So y goes to what? Now I'm going to use the global form for this because I'm talking about the globe. I'm talking about the far horizon, right? So I'm using the global form for this. But something clever happens here, and this is good. This makes life easy, but let me explain how. Plug 1 in here. Notice all these terms are about the same magnitude. This is 1, this term is 2, 2 is about. So we talk about orders of magnitude, 1, 10, 100. 2 is the same order of magnitude 1, okay? The 3 is about 1. Everything is about 1, right? Order of magnitude 1, even the output. Notice what starts happening with 10. I had to shift everything. This first term is about 100, right? Notice the second term, okay, 20, but it's about an order of 10. So the first time is 10 times bigger than the second term. And the first term is 100 times, roughly, of course, right, order of magnitude, roughly 100 times bigger than this term. And the answer is about, well, about the order of the first term, about 100. You don't have to be precise with this, just see the trend. Now, 100, look what happens when I plug in 100. Now, this term is about, well, it is 10,000. Notice how the first term completely swamps what's going on here. This term, that's 200, okay, an order of 100. So the first term is 100 times bigger than the second term and 10,000 times bigger than the third term. So the third term is turning into round-off error. I don't even care about the third term anymore. I mean, who cares? And I'm only talking about 100 here, right? So the first, notice the answer, the result, y value is about the first term. If I plug in 1,000 here, I mean, it's just going crazy, right? I mean, I'm going to infinity with the x values. I'm just scratching the surface. If I plugged in 1,000 here, the first term is going to completely overwhelm and dominate everything. And if I look at 10,000, I mean, the 3 doesn't even stack up anymore. And I'm just getting started, right? When I say to infinity, I'm talking about looking at a million, a billion, a trillion. I don't even know what comes to gigabillion, trillions, whatever. So the only thing I care about is the first term. I mean, the only thing I'm going to care about here is the first term to tell me what's happening. Let's make life easier. Let's make life easier for ourselves, right? So how can we do that? Just throw away the other. I'm only trying to predict what's happening to y, right? Is y getting big? Is y getting positive, negative? I'm just trying to predict that. See, the first term is 10,000. This one's 200, nothing, 3. So just throw away the other two terms. I want to make life easier for myself. So instead of looking at this whole thing, I'm just going to look at the first term. The wiggly equal sign means approximately, right? It's like if I look at you by taking my glasses off. I have glasses, right? Y'all look the same. So I'm only going to look at the first term. And now look, I can get the trend. Instead of looking at everything, I'm just going to look at the first term. So if I put in 10, it's about 100. The y value is about 100. If I put in 100, right, it's going to be about 10,000. If I put in 1,000, it's going to be, wow, I don't even know. I don't care. It's just really big, and it's really positive, right, because it's x squared. I mean, you can do this in your head. If I put in 10,000, okay, it's going to be really big, right? Really big and positive. That's all I care about. You'll see when we draw the picture. I don't have a point. I'm just looking for a trend. An asymptote is a trend. So that's what I mean when I say infinity. Big, huge, ginormous, and positive. All right, so as 1 gets big, as the x values get big, the y values get really big and positive too. And that's what I mean when I say y goes to infinity. Now we'll see how we can use this. Okay, so I want to make this easy. Now if I go x goes to minus infinity, that's going like, well, we'll see. What does y happen? So I want to go the negative direction. So I'm looking at the horizon to the negative side. -1, -10. So see if you can predict what happens. So x goes to minus infinity. See if you can predict what happens to the y values. What is the trend here? Take a minute and see if you can figure it out. Okay, let's look over here. What's the trend in the y values, right? What's happening to the y values? Well, if x is -1, it's 1. If x is -10, it's 100. Again, there's some little bit of round off error, but I'm just looking for the trend. If x is -100, I mean, it's getting big, and it's getting big positive, right? You can, after you do a few of these, you just do it in your head. So what's the trend? Big and plus infinity means big is the infinity, and I really just want to know plus or minus, right? Is it going up or is it going down? So the trend is infinity here. Now I'm going to use this information, this asymptotic information, to compensate for the fact that I don't have a third point. Okay, and you'll see when we draw the picture. So if we graph it, see on the left, I just have the information I need. The zeros, and the asymptotes. So here's my 0, look, this I graph. Here's my 0. Here's my other 0, right? Now look, I use the asymptotic information. X goes to infinity means X gets big, 1, 10, 100, 1,000, a billion. And Y gets big. So on the picture, X is getting big, going out that way. Now my graph only goes to 5, right? I'm talking about going to billions, trillions, gazillions. And the Y is getting bigger, so I'm going out that way. X gets big, Y gets big. I'm heading out in that direction. That's my moonshot. So I'm heading out there. That's what I get from the asymptotics. Notice it's not a point, but it's the next best thing. It's all I have. And let's look at the other side. As X goes to minus infinity means Y goes to infinity. So X is going out this way, right? I'm looking to the horizon that way. And notice the Y's are getting big. So there it is. I'm going up to the moon that way. That's all I have. I'm done. Now you can try, that's all I ask. That's all I ask. Now you can try filling in the remainder, and that's, like in the book, you can kind of fill it in. But you're just guessing. This is all you have. It's not a great answer. But without calculus, it's the best we can do. It's the best we can do. It's all I can do. So it is something. It's not bad, it's not perfect, but it's the best we can do. Now notice if I use the fact that it's a quadratic, I can get the vertex and concavity to get this. But if I don't use the fact that it's a quadratic, this is all I have. And in fact, that's it. That's all I can do. And in fact, that's what the actual picture looks like. Okay, so I get a sense of the shape. Of course, I don't know where the maximum then is. I could guess it has a minimum, right? It has a minimum. But all you can do is guess the shape. I mean, that's all you can do. So that's all we have. I mean, you can't actually okay, it's a quadratic. This one you can. Now let's look at another one. This is more general. Now you see, factoring this to get the zeros, you can't do it in general, right? You'd have to be lucky. It's a cubic. It's a cubic, right? X cubed. So here's the function. That's the global form. Right? That's it. And how do you get the local form? How do you get the break it down? X minus x1. So I have to give it to you. I mean, maybe you could get lucky and guess this. And in the next sections, we're going to explore how to find the local form. So in the next sections, what we're going to do is, given the global form, find the local form. Given the local form, find the global form. How you go back and forth. But generally, in this section, you'll be given the local form. You just, how are you going to get that generally? I mean, you could get lucky and guess it, but it's a problem in general. It's a real problem. So getting the local form from the global form is usually a major battle. It's not something done easily. So I don't expect you to figure this out. I gave it to you here. In the next section, we'll explore some strategy there, how to handle it. And we don't have a complete answer. So just assume I give you this. So here's my equation. I want to turn it into an equation. Solution set. Again, I'm going to find the zeros, and that's what I use the local form for. Okay? I use the local form. So here it is for the zeros. For the zeros, it equals 0, right? The polynomial equals 0. And there's my local form. So it's a times b times c equals 0. A is 0. B is 0. C is 0. And you get your x is minus 4, minus 1, and 3. So that gives me the zeros. Remember, I don't have to calculate. I know the y is 0. That's what it means when you're 0. So I have my 3 points, my zeros. And I can graph those. And again, that's all I have. So in order to compensate, I don't have anything else. I have to look at asymptotes. And for the asymptote, I'm going to use the global form. Okay? I'm going to use the global form. So set it up. You see if you can guess what it's going to be. Notice I'm only going to use the first term. So as x gets big, tell me what's going to happen to the y values. Pause the video and take a shot. See if you can guess. What's going to happen to the y values? Are they going to get big positive, big negative, something else? Give it a shot. Okay, let me jump in. Here's your trend. You don't have to make, you can do this in your head, I think. So if x is 1, that's about 1. 10 cubed is big positive, really big positive, really, really, really big positive. Everything's getting big and positive, and that's infinity, plus infinity. So that's my trend. I'm going to infinity plus. When you say infinity, you mean plus. Okay? And again, you try to do this in your head. It's not meant to be difficult. I mean, really, everything doesn't have to be that hard. How about as x goes to minus infinity? So you're saying minus 1, minus 10, minus 100. What happens to the y value? See if you can guess. Well, don't guess. See if you can figure it out. Okay, here's my table. Minus 1, minus 10, minus 100, minus 10. So minus 10 cubed is, well, big and negative, really big and negative, really, really, really big and negative, ginormous and negative, right? I mean, you're going negative and big, so minus infinity. That's what that means. Okay? So here, there's my information on the left, what I have for my asymptotes. I have the zeros, and I have the information for the asymptotes. So let's graph. I'm going to plot my zeros. Right? Plot my zeros. I'm going to just plot my asymptotes. As x gets big, so x gets positive, y gets huge. Right? The y values get huge, and x is going out that way. The y values are going up, and everything's blowing up that way. Right? That's my moonshot that way. And as x goes to the negative infinity direction, the y's get large in a negative sense. So x is going way out that way, and the y's are going way down there. So the x, y values are going way, way down there. And that's all you have. Again, that's all you can say. Now you can try to put the rest in here. You can try to sketch it in, but this is all you can say for certain. I mean, this is all you really have. It's not a great picture. I mean, it's something, and that's all we have. See, that's why quadratics and lines are so important, linear is so important, because, well, when you get more, it gets tough. And that's it. That's what you have. And you should be able to do this fairly quickly. Given the local form, you should be able to get the zeros really very, very quickly, and the asymptotes very, very quickly. So you should be able to construct something like this very quickly. And that's what it looks like. Right? I mean, I don't expect you to be able to construct. You might be able to guess the waviness here, but that's about all you can do. Okay? So here's it. You should be able to graph it. So I have to give you the local and the global form, right? And you should be able to graph it by plotting its zeros. Plot its zeros quickly. Again, don't make a meal out of this. This should be something you do very quickly. Look, when there's time to work, when we're doing matrices, you're going to work, okay? That's all there is to it. But don't make this a big deal. Get the zeros quickly, get the asymptotes quickly, and just plot it. I mean, just don't make a big deal out of it. Just try to do it quickly. If you have any trouble, let me know. But you should be able to get through this. And again, I don't want you spending, you shouldn't be spending hours on a problem. You should be able to knock this out quickly and efficiently. If not, make sure you talk to me about it. Okay, guys, good luck.